the mic on? Is it working? Okay. I must begin by thanking Morton and Dyalog for the opportunity to do this work.
I don't think your mic is amplifying very much.
I don't know anything about a mic, sorry. Okay. Yeah. Testing 2, 3, 5, 7, 11. Okay. Okay. So, what is this work? Right now it's on Boolean reductions and scans. And what I'm going to talk about today is one particular case, which is not equals reduce on Boolean matrix with a number of columns, which is not a multiple of 8. Okay. The reason it's that way is because the assumption is that arrays with columns which is a multiple of 8 has already been speeded up. Okay, and so this is an extension of a more specialized speed up. So what are basic properties of Boolean arrays in Dyalog? Well, first of all, Boolean arrays are 1 bit per element. And arrays are stored in row major order, 1 bit after the next, first plane, second plane, third plane, and so forth. And within that, then the first row, second row, third row, and so on. And then within the row, it's the consecutive bits are adjacent. And then another basic properties of Boolean arrays is that actually of current machines is that bit access is slower than byte access and word access. Oh, by the way, if you have looked at the stuff on the memory stick, you still have to stay awake for this talk, because since preparing that version, I've discovered things that can be done better than what I said in the version on the memory stick. And finally, another property of machines and architectures and languages is that bitwise operations are available on bytes, half words, and words, and they basically take about the same time. So, in other words, it's nearly as fast to do 8 bits at a time as 16 bits at a time or 32 bits at a time for the Boolean operations that we're interested in. Okay, so let me fire up. So this is version 12.0, the one that is currently publicly available. And I use zero origin. Okay, I begin by doing some benchmarks on the current version of Dyalog. Then I have a workspace called T, and I'll copy in 2 functions. So ran bool generates a Boolean matrix of a random Boolean matrix or Boolean array of the specified shape. And timer does timing, so averaged over the number of times that you specify. Sorry. many times. Okay. So it did the expression 100 times, and the average is about 4 milliseconds. Okay, so I'll do some timings on not equals reduce on yeah. 85. Okay. And in each case, the Boolean array has the same number of elements. So it's basically doing the same number of theoretical Boolean operations, but the times are different. No, sorry. Half of that and double of the other. If I could delete from the session, I would delete that, but anyway. So this is and then just one more. Okay, now what happens if the number of columns is not a multiple of 8? So let's see, 6e4, no, 6.4 e6 divided by, let's say, 14 columns. Okay, so I'll do so it's quite a bit slower than doing it on multiple of 8 columns, even though the array has the same size. So I'll copy this time here, because that's the thing I'm... I know, but my fingers have a different memory timings. So first one is 0.04953. And this one is on version 12.0 on not equals slash of x. So what are some possible ways to speed that up? One is to pad it up to be a multiple of 8 columns. So let's see. Okay, so they are the same. But what do the times look like? Well, you can see that it's slower. And the reason why it's slower is that the interpreter has to do the overtake. The interpreter has to do lots of bit shifts already, so it negates the time gain that it would get in doing the reduction. So that's no good. another way is to do it by converting to integers, which is possible in this case. So let's see if it's any better. 2 mod. Yeah, it's not as good as just doing the straight Boolean reduction, because it's 4953 here and it's 7125. So neither of these ideas work. Well, the key idea that turned out to work is that you know that in a Boolean matrix, no matter how many columns there are, every 8th row it's going to line up. Right? Every 8th row, the rows are byte aligned. The first bit of each row is at a byte boundary. In fact, you can do better than that. If you make the number of columns the least common multiple of the number of columns and 8, then in each of these virtual rows that you make up with that number of columns, the rows are byte aligned. So in other words, if you have 14 columns and you find the LCM of 14 and 8, in this case 56, if you pretend that the matrix has 56 columns, then the rows of this pretend matrix are byte aligned. So let's look at an example. I make a matrix T with 14 rows and 17 rows and 14 columns. Okay. If I make a matrix T1, which is 5 by 56 reshape of T. So I pretend that this matrix has 56 columns. Then at the beginning of each row, the first bit is byte aligned. So if I have a commutative and associative functions such as plus or not equals, I can first do this, and then and this has 56 entries, of course. If I make it back into 14 columns, and then do the reduction on that, it's the same as if I did the reduction on the original matrix. Okay, so on the X, which is the 14-column Boolean array, the not equals reduction of X is the same as 4 by 14 reshape of, go away. is wrong. The wrong reduction. Yeah. There. Okay. So you know that this is a live demo, because if it's a canned demo, that wouldn't have happened. So success. I have a user-defined function which is faster than the primitive. Yeah. And in general, the function I define an operator because I don't trust my typing. So this is a defunds, which is an operator. Sees the number of columns, finds out the LCM of the number of columns in 8. By the way, can I see a show of hands? How many of you have actually used LCM in your work? Good. The primitive. Yeah. Okay. So, okay, and then so M is the number of pretend columns, and D is the required multiple number of rows in this virtual matrix, and M must be divisible by C because it's the LCM, and then you concatenate the identity element of the function at the end, and then reshape it to have N divided by D number of virtual rows, and then do the reduction on that. And this is fast because M is a multiple of 8, being the LCM of 8 as well as LCM of C. And then reshape that to have D by C columns, where C is your original number of columns, and then do the reduction of that. So you still have reduction on an odd number of columns, but D is much smaller than the original number of rows. You know, in my example, it's 4. It can be up to 7, but no more. Okay, so let's see. Okay. What happened? No. Slash. And it works for the communicative and associative functions. such as not equals and equals, and or, and and the speedups work on each of those. Each. No.
Roger, I'm a little unclear. Where are you demonstrating your new code?
This is
or are you just measuring the current system?
This is the current system. But I'm getting to the new code because /0 in the old system is already quite fast, right? More than a factor of 2. So good question. That's section 5 of my talk. Okay, and the last one is or. So basically factor of 7. Now in the new code, I actually did better than this. I'm sorry? Oh, yes. I should have that number memorized, but anyway, it's the shape of x should be 4, 5, 7, 1, 4, 3, 14. Okay, so okay, so so this would be in version 12.1. So 0. What was the original number? So factor of 26. So how does that compare to the other thing that I work on? Use J602. Size. Okay, so x is 4, 5, 7, 1, 4, 3, 2. Not equals reduce x. So what's going on? APO is faster than J. No, but APL has bit Booleans, whereas J has byte Booleans. So APL should be faster than J. So I haven't cheated anybody. If I write the best program that I could in Dyalog, to implement Dyalog, which I believe I have, I write the best C program that I could to do the Boolean reduction in J, it should be the case that APL will be faster than J. Okay. So
how does your stuff compare to what you get by doing essentially the word at a time, aligning and relational that way?
I think it would be faster than what you described, because I don't actually do any shifting or any movement in memory. I just fetch and do. It's a virtual role, so it's just conceptual reshaping. Yeah. Sorry? And conceptual catenating at the end. I don't actually have to catenate. Okay. This is the new version. It was mentioned this morning that testing is very important, and I agree. And the expressive power of APL means that you can test quite thoroughly using expressions that are very concise. So first of all, I'm going to need a little function called assert. So if the argument is not all ones, then it signals assertion failure. But if it's all ones, then it does nothing. Okay, so I'm going to need something to do the assertion on, and I've written a user-defined function that uses something else to do not equals reduce on the first axis. And then I say assert 1, 29. Match. So I've actually tested a huge number of combinations there. No, I didn't mean to show you that. The number of combinations, these are the sizes of matrices that I tested on random Boolean matrices on one line. Okay. Now, I'll give you an APL puzzle. You might have wondered what that plus is doing there. Since I've been away from APL for a while, I couldn't solve this puzzle, and I had to ask John Scholes. So if you know the answer, please keep quiet. If you don't know the answer, ask John Scholes why that plus is necessary.
Which plus? Where's the plus?
Here, this line works, and it's the one I want. And this line is exactly the same, except it doesn't have the plus. Okay. Sorry? It's a function, a defun. Sorry? Yeah. Oh, I loaded the workspace. Nothing's. Sorry? So it sounds like John Scholes will be quite busy explaining it to you. Okay, the question was asked earlier, why don't I just do the /0 script in the interpreter? Well, I could if the interpreter has a functional interface, by which I mean that I can call the APL facilities with arrays and get array results. So let's just, okay, looks like I have 8 minutes. I should be able to do a C implementation of /0. So copy it. I'll put it over here. So this is what I would do if the interpreter has a functional interface. So S is and then C is the number of columns, which is S1. So S points to the shape of the array. So because I'm in C, I have to declare these variables. And then M is the LCM. The LCM is the product divided by the GCD. And I have to tell it what the GCD is for each possible remainder when divided by 8. So if the remainder is 0, it's 8. 1. Remainder is 1 is 1. Remainder is 2. The GCD is 2. Remainder is 3. It's 1 again. Remainder is 4 is 4. Remainder 5 is the GCD is 1. Remainder 6. The GCD is 2. Okay. I'm sorry? Oh, you don't believe me? Wow. You don't have to believe me. You just do 8 GCD of iota 8. There it is. So if I had my wits about me and didn't want to think, and my fingers work, then I just do this. Control insert, right? And then here it's Control V. I don't think so. Oh, okay, it works. Okay, okay, and then D is 4 minutes left. Pressure. D times, and here it's number of rows, which is S0 plus D minus 1 divided by D. Now it gets interesting. So the interpreter would have something called /0 already, and then next function is reshape, v2, and the other argument is the result of a reduction, which is applied on a reshape, and then V2 of n divided by d then the other argument is the original array. Oh, catenation, so cat 0. Y. I'll be lazy and just do 7 because it's a maximum of 7 rows. And because this is specialized for not equals reduced, the identity element is 0. I just hardwire 0 in there. And then an appropriate number of right parens. And then I have these locals that I have to declare, D, M, and then there'll be global definitions that are the same every time. And what are the globals? Will be a file, and first of all I do type def. And then the type of an APL array, the C type of an APL array, which has type, reference count, number of elements, rank, and a pointer to the shape, pointer to the struct, that's capital A, and then a couple of defines. It's a good thing I have this printed out because in the calm of my hotel room I could type this without the cheat sheet, but
I'm are we trying to write this code in detail?
Yeah, I mean I'm proving the point that in 6 minutes I can do the C implementation, which will get you a non-trivial speed up.
And I removed 20 seconds from your time.
Okay. Okay. So and then extern, we use 0. That's an APL array. And then I lied. It's actually NU reduce 0, NU/0, because I didn't want to have to call the general NU/ here. And V2 is a utility that picks 2 C integers and returns an APL array. So, yeah, so that's the C implementation. In fact, in the, is this the new or the old? This is the new. Okay. Ah, that is amusing. Because it's faster than the primitive, even in the new system. No. Oh, well, that's one of the things that I would like to have in Dyalog is instead of my own timer function, to have a more foolproof timer function. Yeah, yeah. Yeah, see, there you go. Or you do it 1,000 times. Yeah. So the point is, in 6 minutes or however many minutes, I could have a C implementation that obtained nearly all of the benefits of the key idea that I described. Okay. J602. What was it in J? The postscript is that, and the difference between what I presented here and what's on the memory stick is that I realized as I was preparing this talk that the same idea can be used to speed up Boolean reduction on arrays with a multiple of 8 columns. Instead of doing on such arrays I can do multiples of the LCM of the words, the number of bytes in a word, and the number of bytes in the argument. So in your APL, if it does things properly, it should, all of these times should be similar modulo the resolution of the timing for suitable definition of similar. Sorry? Yeah, sorry. Yeah. Even then it's not, okay. Yeah. Well, it is, it's all over the place, but E5 32. Yeah. So the idea has been done for not equals. I haven't tested well enough to put it into the other reduction. So if I on not equals, there would be a difference. Yeah, so the idea hasn't been implemented for not equal for equals yet in AND and OR, but it has been done for non equals. Yep. So that is it. Any questions? Yes.
So if you want to port that to 64-bit, you just have to do things like long, or is it completely different?
Yeah, it's
Repeat the question, please.
On 64-bit systems, how would that be different, right? It can be done very quickly because Dyalog, the interpreter, does things in such a way that it doesn't actually use long throughout the interpreter. It defines a type, which is the word type, actually. So on the 64-bit system, it already defines that as the appropriate thing. So instead of, well, it doesn't actually call it I, but it's something else. So instead of that, you do that on 64-bit systems. Okay?
I'm not sure if you're on a lit response method, you can do that. If you're on a lit response method, you can do that 64 bits at a time. Because the alignment is all wrong. But we'll just write it out.
No, you just do the LCM of a different thing. Instead of 8, you do. Yeah. I know it works. Yeah. Okay. Thanks very much.